Swayam Prabha. Digital India. Educated India.
We are going to take advantage of this group-subgroup relation and we are going to work with the subgroup O. Okay. So, you look it up yourself. What is T1U in octahedral OH point group becomes a T1 group in the O point group. So, what I need to do is I need to make the projection operator of T1 operate on say sigma 1. Projection operator of T1 to be operated on sigma 1. Okay. I hope you have drawn the diagram. This is the point group O, okay. But I had promised that I will not make you work out the projection operators for anything after the first problem, right. So, I will just give you the answer, but I strongly suggest that you please work it out yourself later on, otherwise you will not get the practice. So, I will just tell you that when the projection operator of T1 operates on sigma 1, then you get 4 sigma 1 minus sigma 3 minus sigma 4 minus sigma 5 minus sigma 6. Okay. So, that seems to be one of the SALCs. It could be one of the SALCs or it could be a linear sum of some SALCs. Okay. How many SALCs would be there? Why 6? T group, right? T is 3 dimensional, T1. I am only talking about T1U. I am not really talking about A1G and EG anymore. I am focusing on T1U only. So, you should have 3 SLCs of T1U symmetry, and this kind of looks too big to be of T1U symmetry, but we will see. Now, I will tell you that when PT1 operates, of course, I only have one, right? I have to find the others. So, what I will do is I will make this projection operator operate on sigma 2 now, and the answer I get is 4 sigma 2 minus sigma 3 minus sigma 4 minus sigma 5 minus sigma 6. So, now tell me, are they orthogonal to each other? Minus multiplied by minus, fortunately or unfortunately, is plus. So, minus sigma 3 into minus sigma 3 is plus sigma 3 square, which is 1, right. Sigma 3 etc. are all normalized. Sigma 4 into sigma 4 is plus 1, sigma 5 minus sigma 5 minus sigma 5 plus 1, minus sigma 6 into minus sigma 6 is plus 1, and all other terms are 0, right, because sigma 1 is orthogonal to sigma 2, sigma 3, so on and so forth, right. So, the only terms that survive are sigma 3 square plus sigma 4 square plus sigma 5 square plus sigma 6 square, which is equal to 4, not 0, isn't it. So, these cannot be the SALCs, these have to be linear sums of SALCs, right. So, now see, if I have generated these expressions by linear sums of SALCs, then some kind of a linear sum of these should give me back the SLC. right or wrong? Let us say x equal to small a into capital A plus small b into capital B. Okay. Y equal to, now I am at a loss. What will I write? Small a dashed capital A plus small b dashed capital B. Okay. So then x and y are linear sums of a and b. Can you not write linear sums of x and y so that you will get a or b? Understand what I am saying? What I am saying is this. We will use another paper. If x equal to, and now that I am a little wiser, a1a plus b1b and y equal to a2a plus b2b. Can I not write x plus y, something into x plus something into y divided by something and get a, and then something into x minus something into y divided by something equal to b? That is what I will try to do. And looking at this, what I am inclined to do is subtract one from the other. It's attractive because if I subtract one from the other, then I am left with only two terms. Minimum energy pathway. Let's subtract one from the other and let's see what happens. What do I get if I subtract one from the other? I get sigma 1 minus sigma 2. What would be the normalization constant? 1 by root 2. Now, you try doing this same operation with sigma 3 and sigma 4. You want to guess what you will get? What is left? Sigma 5, sigma 6. If you try to do it with sigma 5 and sigma 6, satisfy yourselves, because if I try to work this out, I will definitely dissatisfy yourself at quarter to 7. You get sigma 5 minus sigma 6. Okay. So, maybe these are my SLCs. Let me check. What is the first condition? They should be orthogonal to each other. Are they orthogonal to each other? Of course they are. What would be the second condition? They should conform to T1 symmetry. Or I might even want to go back to the original group and say that they should conform to T1U symmetry. Understand what I am saying? I am saying that they should conform to T1 symmetry in O point group, that is T1U symmetry in OH point group. So, we can check whether that happens or not. You can read it, can't you? Let us work in the O point group. What is it? T1, isn't it? T1. So, remember what they are: sigma 1 minus sigma 2, sigma 3 minus sigma 4, and sigma 5 minus sigma 6. The character of E, of course, is 3. There is no issue with that. What is the character of C3? That also is very easy to see. If you apply C3, then what happens? Then what happens? Sigma 1 becomes, no matter which C3 you apply, all will change places, right? So, sigma 1 minus sigma 3 will not remain sigma 1 minus sigma 3, it will become something else minus something else. So, they change places, character is going to be 0, right? Then what is next? C2. What happens when you apply C2? Sigma 1 and sigma 3 interchange. Sigma 2 and sigma 4 interchange. What do you get? But what does not interchange? 5 and 6 don't interchange. So what is it that you get? Sigma 1 becomes sigma 3, right? So sigma 1 minus sigma 3 becomes what? Sigma 3 minus sigma 1, right? No. What am I saying? So sigma 1, sigma 3 remain the same, right? So what will be the character 1? Right. So sigma 1 remains what it is. Huh? What about sigma 3? Changes and becomes what? And then? So can you work that out? Work out that matrix and see what the character will be? That becomes what? What are you applying? You are applying C3, C2. If you apply C2, then what happens? Sigma 1 minus sigma 2 remains sigma 1 minus sigma 2. What about sigma 3 and sigma 4? What does it become? Sigma 4 minus sigma 3, which is minus sigma 3 minus sigma 4. Sigma 5 minus sigma 6 becomes minus sigma 5 minus sigma 6. So what is the transformation matrix? 1 0 0 0 minus 1 0 0 0 minus 1. What is the character? This is what chi C2 is minus 1, right? Now see. Oh, should have told me. So this is what I have written. All right. The character is minus 1. And it's like Gulliver going from the land of Lilliput to the land of Gargantuans, or whatever the name was. Gulliver's travels as 2, right? So see, we got minus 1. What happens when you apply C4? You work it out, you will get character of 1. When you apply C2, you will get character of minus 1. Okay. So you can satisfy yourself that these 3 actually belong to T1. Okay. So what we have learned then is that we have learned how to generate SLCs for irreducible representations of a higher dimensionality, and while doing that we have learned how to use the group-subgroup relationship. Tomorrow we come back, and so far we have kind of been not so ambitious. We have restricted ourselves to discussion of sigma bonds. So tomorrow we make up for that and we discuss only about pi bonds. And the homework problem that you have, self-study problem that you have, is actually sigma plus pi both, I think. Okay. So we discuss pi bonds tomorrow, and after that, are we all familiar with Huckel's theory? Huckel-Lemmo? Okay. Maybe what we will do is we will recapitulate very, very briefly and let us see if we can discuss naphthalene tomorrow. Let's come at 10:30, because tomorrow our agenda, the thing is I want to discuss as much of naphthalene in one day as possible, otherwise it's no fun. Okay. Please go through Huckel theory if you can tonight from some simple book, Macquarie and Simon or some such place.